Okay, we start up. So, first step today, organize you in groups. Please. Sorry. The student list have been at least partially updated. Anybody know anybody who shouldn't be there, or anybody know someone's missing? Okay. Then we organize you in groups. Let's see how this one works. You haven't received the task yet, so I will go a little bit or talk a little bit about it today, and then later today I'll put out some writing for you, so you will have sort of exercise 3, the objectives clearly for you. Let's see now, where are we? Open. So I have made a cute little MATLAB script that then should take this list and then organize you randomly in student groups, 3 in each group. At the end, maybe one has to be 2 or 4. We'll see what happens. And we run. And if it works, what do you know? 17 groups. So here we should now have a file. First report. So here is all the different groups and how you are to find each other. I have no idea. That's your problem. So you have to sort of find yourself and then agree how to work. I'll put out this one immediately so you can have a look at it. Let's see now.
Will the groups be changed like for every assignment?
Every time.
Okay.
And also I try to organize it so that one person never meets the other one again, just to keep it totally random. Yeah?
How are we sure that everyone on the list is on the class?
We don't, sadly. So here, if you are, say, just 2 students, that's okay. If you are 1, tell me, then we have to rearrange it.
For example, how do I know that the people from my group are having the class? How can I find this out?
Mail them. You have the mail address, or you have the usernames listed here. The first word there, that's the username. So there's Swirl Alpha, student, and UNO.
Okay.
So then you can mail them and ask them, where the heck are you? Or are you here? Other questions? Okay. Let's just create an announcement so you can see it already. First, report exercise. Exercise. That was not right. Here we are. Yeah. So please tell me then if you are find out that you are alone, then we have to reorganize a little bit. Shouldn't be a problem. Okay. When should the deadline be? This Friday? A little short maybe. Let's say next Friday. Is that okay? Shouldn't be too hard, I think. Or do you want the weekend destroyed? Oh, let's put out the deadline for next Friday for this exercise. Now, you have been given 2 exercises, and this exercise 2 sort of essential as a background for now this upcoming exercise 3. I put out a solution for you, and I will go through it a little bit today. So here, solutions to exercises. I haven't written solution 1 yet. See if I can do that ASAP. Solution number 2, here we are. So I will walk you through this one a little bit. So maybe not an entirely fair exercise you got there. We were supposed to compare the result with the DNS, but they got 6.3, and then it turns out that using RANS models you are going to get a different number. Normally a little bit bigger. And I found also another article. People have been playing with different models, and you can see, well, not 5,100 as we had, but small Reynolds numbers, and you can see the range of the results. Totally crazy. So that's always a problem with CFD. How can you tell whether your result is good or bad? Well, from this table here, you have no idea. So you have any numbers here from 4 to 9.5. Crazy. Your problem. Your problem. So I have sort of gone through a little bit here for this. Of course, you can find the viscosity. Then you have the estimates, K, omega, epsilon. How you can get an idea the size of your, say, input value. And then I tried a little bit. I started here with the first standard K epsilon model. And that one quite rapidly went out the window. Can't be used. It's terrible. It gives me totally crazy results. I got some 4 and 4.2 or something like that for the reattachment length. Way off. No matter what I did. So, and this is not a surprise. I mean, standard K epsilon is not built for low Reynolds numbers. And also we know K epsilon has a trouble with reattachment zones. He doesn't like large vortices. He doesn't like curved channels. He doesn't like narrow walls. He's more for, say, simulating around objects instead of inside objects. But we have a nice one, specially made for low Reynolds numbers. Turbulent, but low. This Londe Sharma K epsilon. So that is something I have used. And I tried then first with these estimates for K and epsilon up here, but that didn't really work nicely. Now remember, these are just estimates anyway, so it maybe give you a hint, but definitely not accurate. So you have to sort of play with them. So I tried a little bit here. So I tried first the original mesh. That didn't converge no matter what I did. Quite coarse mesh actually, the one you were given in the exercise. So I multiplied everything by 2, both directions. And with the inlet 0.1, I didn't get any convergence. 0.01, then he converged. Both for epsilon and for K. Then I multiplied it with 3. I got a complete different answer. Also converged. Y plus here should be quite small enough then, so I don't need any wall functions. I could use natural boundary conditions. Then I tried with the K omega SST. That's sort of maybe your first choice. If you have no idea what turbulence model to use, then I would actually suggest the K omega SST. It's quite robust. Should be able to handle most problems nicely. But the inlet omega, that was the question. Originally, it says something dollar internally. I mean, he calculates it himself. So I tried that one. And yes, he converged. And here, I used the fine mesh from up here all the time. Then I played with different values. I think it was 34 from the estimates. And yeah, that one also converged. Actually, most rapid ones. But look at the range from 7.5 to 8.3 as a reattachment length. Which one is right? Trouble. Trouble. I mean, any of these, they have converged, so all of them should be good, right? But that can't be possible. Not this range of answers. So what do we do? What do we do? Today I'm going to talk to you about a procedure that always should be part of your, say, simulation CFD report, the grid convergence index. The philosophy says smaller and smaller delta x's, the closer to the solution. How far can you push this? Of course, you blow the memory in the end, so you can't do it infinitely. But there we have some procedure for at least estimate the error and then say this mesh is good enough, it's adequate. And the procedure, I'll go through it later. And I've done it here for 3 different meshes, multiplied by 2, 2.5, and 3. And then you get some parameters. One parameter here is essential. This P parameter. This reports the apparent order of your schemes, the apparent accuracy of your schemes. We are using second order schemes, period. Hence, the value for P should be close to 2. 2.18, that's very close. If it's 1.5 up to 2.5, that's okay. But if it's 1 or 5, then you're in trouble. Then there's something fishy going on. I'll come back to this one later. Furthermore, I think actually I've done some mistake here. So don't trust this one. I have to change it, I think. I did a little recalculation here that was wrong. Anyhow, what you get in the end is a percentage, an error for your final result, your best result. And of course here it should be the finest mesh, and then I will have my reattachment length as 7.82. With this procedure I can actually then report my result is plus minus a percentage. This is the way it should be done, of course. So it's definitely something important that should be present for any report. Okay. Question C, using fully developed inlet values. So here, to achieve it, I had to sort of stretch the mesh a little bit. I had to use plenty of cells, and I had to stretch it pretty hard to resolve the boundary layer nicely. It's a one-dimensional problem, so I could have used 500 cells for that matter. But I mean 50 was okay. So we'll have a look at one of these later. Simulating a 1D case using cyclic boundary conditions for velocity, for the pressure, for any turbulent quantity. So that should just be a one-dimensional problem. As a driving force, you put in, say, a demand. I want an average velocity of, say, 1, for instance. Then he will set up a pressure gradient for you to achieve that. And you can read out this pressure gradient as a part of the result. So, yeah, that was quite nice. So finding a solution here for a 1D, then you could use that one as an input into your case. That's an inlet value, instead of just using constant values for velocity, turbulent quantities. But my mesh for the original problem, that was not stretched with 50 cells, That was with 30 cells, uniform. Then I sort of have to take the solution I got here, 1D solution, and then interpolate it into a different mesh. Now MATLAB, no sorry, not MATLAB, OpenFOAM has a way to do this, something called map fields. That's a very neat one. You can take solution from one mesh and interpolate it into another mesh. That's quite nice. That's also something you should keep in mind in the future. Say if you have a heavy problem, rather tough one, start with a coarse mesh, get a solution. And then you create a finer mesh, use map fields to interpolate your crude coarse simulation into a finer mesh and use that one as a starting point, and then continue to simulate. You will speed up, say, the process of finding the steady state very much indeed. So map fields, that's a good one. To use it, of course, first you have to create the mesh for a new case. No simulation, you are supposed to interpolate from this fine mesh. And then you just stand in the folder for this, say, coarse mesh here, and execute this command. So he reads from this case. Minus consistent means it's the same geometry, it's the same boundary conditions. So it shouldn't be a problem there. If it's not consistent, well, that's a quite different story. So it should be. And then I just take from the latest time as a source up here. Having done this, I will now have a 0 folder in this case, where I have sort of tabulated the result. So he may now look something like, well, actually not something like this. Here, I have now taken the interpolated results in my 0 folder from this coarse 1D case, which now is my input. And then I just copy velocity and the different quantities. And then you paste them as inlet. Now you see here it's a 0U velocity, 0U file in the big real simulation. You want a velocity profile as an inlet, not just one constant number. So there, as an inlet type, is fixed value, but now the value is a non-uniform list as a vector. And then 30 values, and then just punched in directly. Paste it. For k omega epsilon, it's going to read scalar, it's not a vector, and then it's just one numbers, not 3 numbers for u, v, and w, of course. So that is how this one is done. And so I tried this with both for the Lon de Sharma, k epsilon, and for the k omega SST. And I got 8 and I got 7.3. Both converged nicely, which is right. Not easy to tell, is it? Then sort of as a final check, remember you have a one-dimensional case. You have 0 velocity at the bottom and you have a symmetry plane at the top. And the velocity profile you get should compare quite nicely with the law of the wall. Okay, so here you have the velocity profiles. And I mean, they look quite nicely. They are turbulent. It's not a parabola, it's a laminar solution. So you have sort of a sharp shoulder here and then quite flat in the center region. And the higher the Reynolds number, the sharper the shoulder is going to be. And you see, not much difference between these two. But the small difference there, you will see the effect of it is actually quite crucial. Plot them in the law of the wall diagram. Y plus versus y plus. There you see what happens. Here, this k omega SST fails badly, very, very bad indeed. But the k epsilon, Londe-Sharma k epsilon, fits okay. You start with the viscous sublayer up to 10 plus units, and then you have a buffer zone, and then from 30, where are we here, 30, then at least he hits the log wall. He doesn't get the inclination precise, but at least much, much better than the k omega. So from this one, I take the k omega SST and I throw it out the window. It's not good. Maybe you could have done the 1D better, more cells, better resolvement. I'm not sure if you will succeed. I think the standard k omega SST really not built for low Reynolds number problems. Turbulent, of course, but low. So he overdo it. So as a final conclusion for exercise 2, I say the Londe-Sharma k epsilon is the best, and this is my answer. Then I should have, of course, have done a grid convergence index here as well, so I could have the answer plus minus some percentage. That would be perfect. This solution, as you can see, is not written as a nice report actually, but you can think of it as how you should report your exercise 3, sort of in the same way. You don't have to write a nice report, you don't have to write full sentences, as long as I can understand what the heck you are doing. And the important point with the exercise is to show me, convince me that you have understood the different learning objectives. And I will write them out for you, so you'll have it on your exercise 3. What's the aim for this exercise 3? Of course, turbulence models, Y plus, GCI coming in, and also what should you aim for? Talk more about that one later. Any questions so far? That's okay. So be aware, I think my GCI was wrong. I have to check it later today. But else, I think this solution should be okay. Together with this recipe here, you have been given then a whole bunch of the different scripts. So I think this one was k epsilon, this one was k omega, and then the 1D setups. I mean, I just zipped down the different cases. Using foam clean tutorials, so it's a very clean case. You have to run block mesh and then simple foam to execute it. But you see you have a whole bunch of them. So here, for instance, that's the the inlet one-dimensional for k epsilon. And then I had to create, this was with 50 cells stretched. Then I had to create another one with 30 cells uniform, so I can interpolate the solution that one into that one. And then finally read the result here, the interpolated result, and then put them in as an inlet value here, as velocity profiles, k profiles, omega profiles, and so on. So you see it when you sort of unzip these different ones. K epsilon and the k omega SST. So you have everything, everything here. Yeah, there may be one thing that I haven't shown you. Well, we can rapidly do that, I think. Let's see. Here we are. I just want to show you one of these 1D simulations. Where are we? Here we are. Inlet, well, we can take the K epsilon, why not? Here we are. So, block mesh. So you see, I have 50 cells, and it's a one-dimensional problem. Still, I have the bounding box. It goes from 0 to 1 in both the x and the y direction. Well, the y direction, it should be 1. I mean, that was the size of our inlet anyway. So yeah, that had to be the same. But that shows also 1 meter here in the x direction, which is rather stupid. I mean, I just have one cell in the x direction. Nothing changes there. But still, you need a dimension there. And the z, I just use 10 centimeters. Okay. Then the driving force for my problem, that was given in this file FV options here. So you just sort of give a driving force into the problem to achieve average velocity of 1 in the x direction. But I want this driving force afterwards. How big is this driving force? Well, let's see. It goes quite fast, even with 50 cells, no problem. So here you have it, pressure gradient source. U bar is 1, pressure gradient equals, and then I get a number. This is the pressure gradient. Ah, beautiful. What do I need that one for? Well, let's have a look. The solution, well, we can have a look, of course. Parafoam. Here we go. And we go to the end. And the pressure, if you look at the scale for the pressure, it looks very nice. But it is machine accuracy. Of course, the pressure doesn't do anything. No velocity in the y direction. It's not possible with only one cell there. So, and you have a solid wall at the bottom. So the pressure, he doesn't do anything. This is just a nice numerical noise. Velocity, now we're talking. So you have a nice velocity profile here. 0 on the wall and then fairly steady in the center region. You have, and this is maybe the important point. Here you get the values for K and epsilon for a fully developed flow. And yes, he has a profile. And if you look at the numbers here, maximum number 0.001, okay, then you can use that one, or maybe even smaller, as an average epsilon to find what the heck should I put at the inlet. This will be one way to do it. Instead of not just give the detailed profile, but at least find an average value. So roughly maybe here. Same goes for the epsilon. No, sorry, the K. Yeah, it's sort of in the same range as the epsilon. And if you want it a little bit more in detail, you can take plot of a line along the center here somewhere. Let's see now, that should be x.5, set 0, x.5, set 0, and apply. Then we will have something like this. So here, yes, you get the nice velocity profile. Of course, now he plots U magnitude. But of course, that's the only velocity you have. So whether you plot U magnitude or Ux, you won't see any difference. Of course not. If you remove that one, then you sort of have some other quantities here. Let's see now, the pressure we don't need. Can get rid of that one. So here you now have the profiles for a fully developed turbulent flow for the K epsilon model. So you see the epsilon dangerously sharp close to the wall. You have to resolve that one actually to get it more or less correct. The K a little bit further out, but not much. So as an average value here for K, I would suggest then maybe 0.0065, maybe here somewhere. For epsilon, maybe a little lower, 0.02. That should be good average guesses if you don't want to use the entire profiles as inlet values. Okay, any questions to that one? So you have these scripts on as a solution, so you can have a look at them. Now let's have a look at this number we got here. Pressure gradient source. What do we need that one for? Well, let's have a look. So here was our problem. Solid wall. We have a symmetry plane up in the sky, and yes, you get a velocity profile, turbulent velocity profile, looking something like that. Okay. Here I have a length, and here I have a height, like that. Now, for solving the Navier-Stokes for such a problem, well, you're going to need a driving force, of course we need. And what is the driving force? Well, it's going to be a pressure difference. Not the pressure you are simulating, but some external driving force given as a constant pressure gradient. So let's see now. To the left here I have the pressure P1, and here I have a pressure P2. Something like that. And then, if you want it correctly, you have a depth in the Z direction, depth B or something. Now you do a control volume analysis. And your control volume, don't we have any colors here? Blue? Well, we can try. Your control volume should then cover your entire computational domain. It should not go through the bottom wall, but you glue it towards the wall there. And now you look at the forces, sum of forces in the x direction. What's the sum of the forces acting on this one? First of all, you have the pressure or pressure difference. A pressure will act on, say, the faces here. So P1 minus P2 multiplied with, and then you have the area, H, and then the depth inside into the blackboard. That is the driving force. Has to balance what? It has to balance the shear stress that is acting down here from the wall on the flow. So down here, yes, we need the shear stress. And I remember, I have only one single cell in the x direction, so it's just one single number. Beautiful. So here I have some wall shear stress, and then what's the rule here? Shear stress, the same dimension as pressure. So to get a force, I have to multiply with an area. What area? Well, that's the area that's wet, the bottom. So I'll have to multiply with the length and then the width. And now, according to Newton, I don't have any more forces. No gravity, no nothing else. Sum of forces equals what? Mass times acceleration. I don't have any acceleration. It's a steady state solution. So no acceleration in this solution, hence the sum of forces equals 0. So there you see it. The depth does not matter, of course not. And now from this, say, simple force balance, I can find my shear stress. And that should now be something like my pressure difference divided by L. multiplied by h. Something like that. Okay. What did we get from our simulation? We got the pressure gradient. What do you know? Looks something like this, right? Okay. So there you will have your pressure gradient, dp dx. But remember one thing. In open foam, when you're doing incompressible simulations, incompressible, he uses a sort of a strange pressure. It's not the dimension for the pressure. This is actually the real pressure scaled with the density. The density doesn't appear in our equations at all when it's incompressible. That's also why we specify the kinematic viscosity, not the dynamic viscosity. Kinematic viscosity, that's just meters squared per second. The dynamic, that's kilo over meter second. That's something else, something we have to do when it comes to compressible cases. Okay, now what? I have my shear stress, and I have this number, or actually the pressure divided by the density. What do I need it for? I need it because I want to calculate, say, my scaling, the y plus scale. Y plus, it was given as what? Well, there you had a shear velocity, u tau or u star or whatever you call it, multiplied with the real distance y divided by the kinematic viscosity. This u tau, by definition, equals square root of, and then you have the tau, the shear stress at the wall, divided by the density. This is your scaling velocity. So it's not actually a velocity you can see, but you sort of use the shear stress here to invent a velocity scale locally down here. Okay? And now, what are we going to need? I need tau divided by the density. Okay, let's just divide by the density then. Okay, there you have it. So the value here will now be exactly what OpenFOAM reports as a driving force, the pressure gradient, even here already divided by the density, so that's just this number directly. My h was 1 meter, so he disappears. So you just you just take square root of that number, and then you have your velocity scale. That one you're going to need when you later is going to plot, say, the velocity in a comparison with the law of the wall. Then you have to know the y plus and the u plus. I mean, the definition there, what was it? U plus, that is the real velocity, say in the x direction, and then you scaled with this shear stress or shear velocity. So yeah, you need them. And of course, all of you knew this already. Kindergarten stuff, right? No problem. Doing such a, say, a control volume analysis might be a very, very good idea for any problem. Keep that one in the back of your head. We might need it later. Here it was very easy, but it can be more tricky. Coming back to that one later. Any questions? Then after the break, I will go through this recipe for the grid convergence index to ensure that we have a nice resolved mesh. For those of you who took the introduction to CFD last semester, you know this already. So you may take early lunch. For the rest of you, please be seated. No questions?